Central to the understanding of linear manifold learning is understanding the role that linear transforms play in this process. In this video, we will define what is meant by linear transforms and revise the topic of eigenvector decomposition and vector spaces. Mathematically, a linear transform is a function which satisfies the properties of additivity and scalar multiplication, whilst preserving the origin. This means that if you sum two vectors and then transform them, you'll get the same result as if you'd transformed each individual vector and then summed the result. And the same is true for scalar multiplication. It's equivalent whether you do it before or after the transformation. In practical terms, however, what we really need to know is that the action of a matrix on a vector is a linear transform. For example, if we consider this 2 by 2 matrix with a 3 and a 1 on the diagonal, it acts on a vector xy by transforming that data point to a new vector x prime y prime, where x prime equals 3 times x plus 0 times y, and y prime equals 0 times x plus 1 times y. This action represents a scale in the x direction by a factor of 3, such that if we had a set of data points that made up a square, and we multiplied them all by that same transformation matrix, it would scale or stretch our square into a rectangle. Eigenvectors of a given linear transform are defined as the directions which remain unchanged with the exception of a scale factor following the application of a transform. For example, in this operation performed on the Mona Lisa, the red vector, originally in the y direction, changes under the operation of the transform, whereas the blue arrow in the direction of the x-axis does not. In this case, the blue vector is an eigenvector. This allows us to define an eigenvector V of a matrix A in the following way, as the action of A on V returns just a scaled version of itself, where the scaling factor is given by the constant lambda. This then gives us a way to estimate the eigenvectors V and the values lambda by determining the characteristic equation. We do this by showing that if we brought everything onto one side of the equation and bring the common factor V outside of the brackets, then the product here must be 0. And as the eigenvectors are non-zero by definition, this means that instead A minus lambda I, or more specifically its determinant, indicated by these parallel lines, must be 0. Note I here is the identity matrix with ones on the diagonal. So what we want to do is estimate the lambdas that make this determinant return 0. So let's say that our matrix B is a 2 by 2 matrix with values A and B on the top row and D and C on the bottom row. The determinant of any 2 by 2 matrix is straightforwardly estimated as AC minus BD. Thus, for our specific example, where we have a matrix A with 3 and 1 on the diagonal, and we want to subtract lambda times the identity matrix, where the identity matrix has 1s on the diagonal, this gives us the following determinant, which, because there are no off-diagonal terms, gives us just the AC part, which returns 3 minus lambda times 1 minus lambda. This shows us that the roots of the characteristic polynomial, the values for which the determinant are 0, are given when either lambda equals 3 or lambda equals 1. So now that we have our eigenvalues, we can estimate our eigenvectors, starting with the case that lambda equals 3. So the first thing we need to do is substitute in 3 for lambda in this equation. This gives us 3 minus 3 and 1 minus 3 on the diagonal. We then need to solve for the series of equations in order to estimate V1 and V2 in order to return our eigenvector. So writing out these equations, we get 3 minus 3 is 0, so 0 times V1 plus 0 times V2 equals 0. So clearly this is not very informative. However, the bottom row gives us 0 times V1 minus 2 times V2 equals 0, which, together with the additional constraint that our eigenvector must be non-zero, can only work out if V1 is non-zero, but V2 is 0. because otherwise you'll have, if v2 wasn't 0, you'd have the solution that 2 times something equals 0, which is obviously not true. And this therefore means that the eigenvector corresponding to the eigenvalue lambda 3 must have the form v equals 1, 0. Note that by choosing the magnitude of the x component of v as 1 is actually arbitrary, since any constant multiple of our eigenvector will also be an eigenvector. Now for lambda equals 1, we perform the same operation, but this time we substitute lambda equals 1. This gives us a series of equations of 2v1 minus 0v2 equals 0 for the top row, and 0 times v1 plus 0 times v2 for the second row. So we ignore the second row and look at the top row. And as before, the only way that this can be solved is by having a non-zero value for v2 and 0 value for v1. So therefore, the eigenvector corresponding to the eigenvalue lambda equals 1 can be any constant multiple of the vector 0, 1. So this represents a stretch in the y-axis by a factor 1, whereas this represents a stretch in the x-axis by a factor 3, where the scale of the operation is determined by the eigenvalue. So, recapping the demonstration that we've already seen, this linear transform with a 3 and a 1 on the diagonal has eigenvalues 3 and 1, and eigenvectors in the x direction and the y direction, and thus it represents a stretch in x by a factor of 3 and a stretch in y of a factor of 1. In other words, it's staying constant in the y direction and stretching by 3 in the x direction. So what then happens when we have off-diagonal terms? So this time we do have a BD term where b times d is 1 times 1. So when we estimate our determinant, this gives us 2 minus lambda times 2 minus lambda minus our off-diagonal term, minus 1. So now we need to refactorize our characteristic polynomial to account for this term. We do this by first multiplying the factorized terms out to give us lambda squared minus 4 lambda plus 4. Then we subtract this off-diagonal term minus 1 to give us lambda squared minus 4 lambda plus 3. This will then refactorize as 3 minus lambda and 1 minus lambda, which is what we had before, because 3 times 1 is 3 and minus 3 minus 1 is minus 4. So we get the same eigenvalues that we had for the previous diagonal matrix. So we can now go through the process of estimating the eigenvectors again, where now that we have off-diagonal terms, nothing is multiplied by 0. So instead, this time for lambda 3, we get 2 minus 3 and 2 minus 3 on the diagonal. When we multiply out these equations, it returns minus v1 plus v2 equals 0 for the top row, and v1 minus v2 equals 0 when multiplying out the second row, which, after rearranging, tells us that v1 must be equal to v2. So as this is arbitrary up to a constant, we can define the eigenvector corresponding to the eigenvalue 3 for this matrix as the eigenvector 1, 1. Similarly, for lambda equals 1, we can go through the same process, and this time it tells us that v1 equals minus v2, and so our eigenvector corresponding to lambda equals 1 must be some constant multiple, or any constant multiple of the eigenvector 1 minus 1.
Therefore, these two matrices represent the same operation on a different coordinate basis or axes, where the axes are defined by the eigenvectors of the transformation. Projecting our transformation matrix onto this basis will therefore diagonalize this transform, as shown through the operations in this box. This changes the operation from a stretch on the diagonal to a stretch in x and y. We can therefore also represent our data in this basis by projecting it onto the eigenvectors of the transformation. This is seen as a rotation of the coordinate bases. For example, as shown here, the standard basis xy and the rotated basis x prime y prime are two equally valid coordinate bases for this 2D vector space. One very important final point to remember as we move on to PCA is that PCA expects unit eigenvectors. This means that when you're asked to return eigenvectors of PCA, you must first normalize them. You do this by dividing through by the vector magnitude estimated using Pythagoras' theorem. So in summary, the action of a matrix on a vector space is a linear transform, where eigenvectors are vectors which remain unchanged with the exception of a scale factor following this transformation, and therefore they represent a new basis in which that transformation is diagonalized. To estimate eigenvectors and eigenvalues, you must solve the characteristic equation, where you will be expected to know how to do this by hand for 2x2 matrices. Don't forget, therefore, that PCA requires unit eigenvectors, and so if you're asked to present your eigenvectors in this form, you will need to normalize them. And finally, data can be projected onto this basis through pre-multiplying the data matrix with the matrix of eigenvectors. Now go on to complete the Keats quiz before moving on to the next video lecture.